Problem 28 says let g be a continuously differentiable function with g of 1 being 6, g prime of 1 equaling 3. What is the limit of this mess? Okay, so let's kind of take a little look at this limit here. They always try to make the very, like this last problem on the multiple choice section be particularly riddly. Anyway, so I'm just going to copy the limit here. You know, and as I'm copying it, I'm kind of brainstorming a little bit. So the first thing I'm going to think about is like, hey, what was the first thing I was taught about limits? It was try to treat it like a function value, you know, and if it shouldn't be a function value, math will tell you no. So let's just take a second and like see what happens if we treat it like a function value. If we did, then you just replace all the x's with 1s. So we'd have the integral from 1 to 1 of g of t dt divided by g of 1 minus 6. And what would these things equal? Well, think about area for a second. You have the area bounded between the graph of g and the x-axis, starting at 1 and stopping at 1. So that would be exactly 0 area. So the top, you definitely get 0. On the bottom, since they said g of 1 was 6, you'd get 6 minus 6, which is 0, which is kind of good news, kind of bad news. I now know, though, that since I have an indeterminate form, I can use L'Hopital's rule on it. So I'm just going to like say that was sort of a waste of time, but sort of not. And then I'm going to apply L'Hopital's rule. And how do I apply L'Hopital's rule? Well, I still have the limit as x approaches 1, and basically I just need to take the derivative of the top and the bottom separately. So for now, I'm just going to go ahead and give a little dirtbag IOU on the derivatives. Just say, like, I promise I'll do it, but I haven't done it yet. And then really quick on the top here, if you ever see an integral with bounds that have like some functions involved and a derivative on the outside, then what I want you to do is just work from the inside out. So you're going to go ahead and just do antiderivative. Antiderivative of little g is big G, just kind of meaning whatever the antiderivative was. Plug in upper lower bounds, subtract the results, and then we'll take the derivative next. Okay, so you're going to use the fundamental theorem of calculus on this part, and then in a second step you'll take the derivative. So here's what that would look like. Limit as x approaches 1 of d dx has to just sit there and wait. And then this integral using the fundamental theorem of calculus would be big G of x minus big G of 1. Okay, and then let's do the derivative of the bottom. That's easier. D dx of g of x would be g prime of x. D dx of 6 would just be 0. So I'll just show that I thought that out. But if you don't write minus 0, it's totally fine. Okay, now before you move on, please don't do anything wacko with g of 1. Please remember, if you put a constant into any function ever, you get a constant out. So g of 1, if it could talk to you, it would say, hi, I'm a constant. So when you take the derivative, make sure you get 0 for that derivative. So what would we now have then on the top? D dx of big G is just little g again. And d dx of that constant is 0, so I'll show that I thought it out. And then on the bottom, you have g prime of x or g prime of x minus 0, same thing. Now let's go back to the first thing we're taught about limits. If you can treat it like a function rule, you probably should. So we would end up with g of 1 on the top and g prime of 1 on the bottom. And what did they say g of 1 was? G of 1 was 6. G prime of 1 was 3. And so it looks like the answer ends up being 2, or D.